All right. So we're learning a lot about a new word called stoichiometry. Stoichiometry. And although it sounds like a tasty German treat, the word stoichiometry means the relationship between moles of material, either moles of atoms in a molecule of a compound, a mole of atoms per mole of compound, or we can refer to moles of chemicals, like in this case, carbon monoxide, to moles of carbon dioxide, or moles of reactants to moles of products. And we do this through the coefficient, So this coefficient here is 2. This coefficient here, if there's no coefficient, what's the coefficient?
1.
1, right, and this coefficient is 2 there. So we can make what we call stoichiometric statements. Can you say that? Stoichiometric statements?
Stoichiometric statement.
Very good. We can make stoichiometric statements about, like we did last time, moles of atoms per moles of compound, or in this case, moles of reactant for moles of product. Okay? So here's a chemical reaction. Nitrogen gas combining with 3 hydrogen gases to form 2 ammonia. NH3 is called ammonia. Some chemicals, like NH3 or H2O, they have common names because they were invented or discovered a long time ago, realized a long time ago. So we have to kind of get used to some of those. Like water, we don't ever call dihydrogen monoxide. And this one we don't call nitrogen trihydride, okay? This one is always called ammonia. But we'll remind you long enough that eventually you'll remember. So what's the ratio between nitrogen and hydrogen? What's the stoichiometric relationship?
What?
What's the stoichiometric relationship between nitrogen and hydrogen in this chemical reaction?
Does that mean what's the same about them?
No, it means what's the coefficient in front of each of them?
Oh, nitrogen is 1
Mm-hmm.
and hydrogen is 3.
That's right. So essentially what we are seeing is we can make conversion factors where we say, 1 mole of nitrogen gas combines for every 3 moles of hydrogen gas. Or I could flip that around, 3 moles of hydrogen for every 1 mole of nitrogen gas. And that's basically saying, in this reaction, if I want to consume a mole of nitrogen, I need 3 moles of hydrogen. And if I have 3 moles of hydrogen, I need to make sure I have 1 mole of nitrogen to have this reaction occur. Okay, what about nitrogen to ammonia?
One mole equals 2 moles.
That's right. 1 mole of nitrogen to 2 moles of ammonia. Can you say ammonia?
Ammonia.
Very good. How about hydrogen to ammonia? What's the stoichiometric relationship there?
3 hydrogen moles for 2 ammonium.
Very good. Ammonia. Excellent job. So here's a chemical reaction, same chemical reaction. And the question is, based on this chemical reaction, how many moles of nitrogen gas will be used if 2.3 moles of ammonia were produced? All right, so I can't answer this question with our method because to the right of the equal sign, I'm trying to answer the question, what? What is the question I'm trying to answer? Can you read that question? What is it?
For the reaction of N plus 3 hydrogen equals ammonium, how many moles of nitrogen are used when 2.3 moles of ammonium are produced?
Yes, so what goes to the right of the equal sign here?
Moles.
Moles of what?
Nitrogen.
Moles of nitrogen gas. And what do I start with over here?
NH.
That's right. 2.3 moles of ammonia, NH3. What has to go down here?
Moles of ammonia.
Very good. Moles of ammonia. Now, let me remind you of we saw this, we've seen this before. This is called the ammonium ion, but NH3 is by itself is just ammonia. So we have ammonium, and this is ammonia. Kind of confusing. So if moles of ammonia go on the bottom, what needs to go on top here?
Moles of nitrogen.
All right, and what is the relationship between moles of nitrogen and moles of ammonia?
Moles of nitrogen has 1 mole. For every 1 mole of nitrogen, there's 2 moles of ammonia.
Very good, ammonia. So to answer the question, I just take the 2.3 and divide by the 2. And that's going to give me the moles of nitrogen gas required. All right, here's another one. If 0.575 moles of carbon dioxide is produced by the combustion of propane. Now, do you remember what combustion means?
Another word of combining something.
Combining something with oxygen. Very good. It's combining something with oxygen, or essentially burning it, right? When you combine something with oxygen and a little bit of heat, it will burn. So if we burn 0.575, if 0.575 moles of carbon dioxide is produced by the combustion of propane, that's C3H8, how many moles of oxygen are consumed? So what goes to the right of my equal sign?
Oxygen.
That's right. What of oxygen?
Consumed?
Yeah, but I mean, what are my units? How many what? Grams of oxygen?
Mole.
Moles. Very good. How many moles of oxygen are consumed? What goes to the top left here?
0.575 moles of carbon.
Carbon dioxide, right?
All right.
That's how many moles of carbon dioxide was produced. And the question is, how many moles of oxygen are consumed? So, can you look at this equation and see the molar ratio between oxygen and carbon dioxide?
There's oxygen. There's an extra oxygen.
Well, all we need is the numbers in front of the different reagents. So we have 5 in front of the moles of oxygen. So that goes here. And what numbers in front of the moles of carbon dioxide?
3.
3. Very good. So 0.575 times 5 divided by 3 will tell me how many moles of oxygen I needed to consume to perform that reaction. Okay, did you follow that?
Yeah.
Good. So what we're doing here is we're using the stoichiometry of the equation. I like to call it the power of the equation, because if you didn't have the equation, the balanced equation, notice that you had to have these equations balanced with the right numbers in front. If you didn't have these equations, you couldn't answer these questions. So The power of a balanced equation is great to have. Now, we can also answer questions like this. How many grams of this compound? Can you tell me the name of this compound? Al is element 26,
No, that's iron.
13. It's not opening on my computer. My periodic
And
aluminum. Yeah.
aluminum.
Huh. My periodic table is not opening. Oh, there it is. Okay, so aluminum, element 13, and oxygen. So what's the name of the compound here?
Aluminum oxide?
Very good. Aluminum oxide. Excellent. So how many grams of aluminum oxide are produced when 41.5 grams of aluminum react? And now this is a great example of a question because this is the kind of thing that chemists need to do all the time. How much aluminum oxide am I going to get if I react 41.5 grams of aluminum? All right. So what goes to the right of my equal sign?
Grams of aluminum?
Is that the question? What is the question that they're asking?
How many grams of Al oxygen, aluminum oxygen?
That's right. How many grams of aluminum oxide? Great. What do we start with at the top left?
Al 41.5 Al.
0.5, and that's grams of Al, right?
Right.
Now, to relate aluminum, see, we need to relate this aluminum, because that's what they're telling us. You have 41.5 grams of this aluminum. To relate that aluminum to this aluminum oxide over here, we need to go and get the power of the equation. But we can't get it if we're in grams. We need to go to the land of the moles. You know why you go to the land of the moles?
You times it by 27.
Good. 27, and you don't, but that's grams of aluminum and moles of aluminum. So where does the 27 go? Up top or down below?
It's meant to go up top, right?
No, you just have to look at these units, wherever the units are. So we need grams of aluminum down below. So the grams, because there's 27 grams for 1 mole, right?
I thought you were meant to times it and then it gets it.
No, see, that when we're in grams of aluminum, this is how we know what we need to do because we need to get rid of those units. So we need to get 1 mole of aluminum. Now we're in moles of aluminum, and we'd like to go to moles of aluminum oxide. Do you know the molar ratio of those two? We're in the land of the moles now, so we can use the power of the equation. That's why we go to the land of the moles, to get the power of the equation. What's the equation say?
2.
2 for which? The top or the bottom?
Bottom.
Bottom. And what's on top?
1.
1. Very good. Now we can go out of the land of the moles because we got the power of the equation there. We can go out of the land of the moles and go back to grams of aluminum oxide. Okay. Do you know the molar mass of aluminum oxide? What values go here? Here's a hint. It's down here.
102.
102. Does that go on top or bottom?
Top.
Top. Very good. 102 grams for every 1 mole. Fabulous. So we figured out that we can go from aluminum grams to the land of the moles. We go to the land of the moles because it's like Disneyland, but it's free. And there you can get the power of the equation. Once you get the power of the equation, you can go back to the land of grams and get your answer. All right? Very good. Here's another one. How many moles of KOH? Can you find the name of that compound for me? KOH?
KOH. Is that on the back?
I think the OH is on the back, yeah. K is element number 11? No, 19. K is element 19. And the OH is on the back.
Oh. K. Wait, K is element what?
19.
Oh, potassium.
Very good. Potassium.
Hydroxide.
Hydroxide. Excellent job. Very good. So how many moles of potassium hydroxide are required to make 3 moles of, what's this one called?
Potassium. Sulfate.
Very good. Potassium sulfate. What do we put for our equal sign here? What do we put to the right of our equal sign?
Moles of K2SO4.
Is that what we're asking? Read the question to yourself. What's it say? How many moles?
KOH.
Which is potassium hydroxide. Very good. So, moles of potassium hydroxide, we start with top left. I'll bet it's the 3.0 moles of potassium sulfate. Okay, and then we have to go moles of K2SO4 to moles of KOH. Right? What's the ratio? What's the stoichiometric ratio?
KOH is 1.
1.
Oh no, 2.
2.
KSO4. And 1.
2, and potassium sulfate is 1. So, what is our answer? A, B, C, or D?
B.
B as in dog?
B as in boy.
Okay, very good. 6 moles. Excellent job. Okay, so here's another one you can practice. We're not going to practice this one right now, but I'm going to let the folks at home take a second, try to practice it, and do it in 3 seconds because I'm going to answer the question. Push pause so you can get a good practice. 3, 2, 1. Okay, here's the answer. D. Excellent job. I'll show everybody at home how to do this one. How many grams of water is the question. So to the right of the equal sign, I write grams of water. And then I start with 1.2 grams of H2SO4. 1.2 grams of H2SO4. I go from grams of H2SO4. Where do I go? The land of the moles, right? And then I go moles of H2SO4 to moles of H2O, right? And then I can go from moles of H2O. What am I doing in the land of the moles? What am I trying to do in the land of the moles, Tom?
Moles of H2SO4. One is the first, no, second.
One here for H2SO4.
Why is there two? Oh, yeah. And the other one.
Moles of water is one also.
Yeah.
Do you see it right there?
That's not it. That's H2SO4.
Here's H2SO4. That's one. But then the other one,
right there.
yeah, the one is H2SO4, like you said. But what's water? H2O. Huh?
Top left.
Over here? Oh, here.
One. Yeah.
That's one. Very good. How about this one?
H2O2.
Two. Very good. All right. And then there's 18 grams of water for every mole of water. Okay. Very good. Now,
Pause.
what's that?
Can we pause?
Say it again.
Can we pause?
Oh, yeah. All right. Now, we've already done balancing. And so there's a little portion in the book that talks again about balancing. But it's just a reminder that when you try to balance an equation, you can only adjust the prefixes here. So we're not going to go over this again because we practiced it before, but we can see that there's one barium on each side. On the left, you see two hydroxides and only one over here. So we're going to need a 2 here, and then that's going to match up with the 2 sodiums, right? So balancing is pretty much, we practiced it already. If you have troubles with it, you should keep practicing until you can do it well, because it's necessary. If we don't have a balanced equation, then we can't use the power of the equation, right? Okay. So now we're going to introduce a concept which is very, very important. It's called limiting reagent. Limiting reagent. And it's kind of like when you're making something that has different parts. Like if you're making peanut butter and jelly, and you have lots of peanut butter and lots of jelly, if you only have 2 pieces of bread, it doesn't matter how much peanut butter and how much jelly you have. You can't make more than one sandwich. Does that make sense?
Yeah.
Okay. So if I have 4 pieces of bread, how many sandwiches can I make?
Do you have peanut butter and jelly already?
Yeah, good question. If I have lots of peanut butter, lots of jelly, and 4 pieces of bread, how many sandwiches?
2.
2 sandwiches. Right. Okay, but what if I have a whole lot? If I have a whole truckload of peanut butter, can I make more peanut butter sandwiches if I have 4 pieces of bread?
No.
All right. This is called limiting reagent because the bread is limiting. All right. If I have 5 loaves of bread and each loaf has 30 slices, so I have 6 times 5 times 30, 150 slices of bread, but I don't have any jelly. I have lots of peanut butter. Can I make any peanut butter and jelly sandwiches?
No.
What's the limiting reagent then?
Jelly.
The jelly. That's right. So whatever is running out is our limiting reagent, right? Okay, so Here's the chemical reaction, the one we just kind of were playing with. Nitrogen gas, hydrogen gas, and ammonia. The stoichiometry suggests that one of these for every 3 of these to make 2 of these. So what happens if the proportions are not met? What happens if I have 10 hydrogens but no nitrogen? Can I make some ammonia?
No.
I can't. I can't make some ammonia. What if I have 5 nitrogens, 3 hydrogens? How many ammonia can I make?
One.
That's right. That's right. If I only, or sorry, 2, right? 2 for every 3 hydrogens. And the way that we answer that question is we ask the question, all right, if I have 5 nitrogen and 3 hydrogen, how many ammonia? If I want to know how many ammonia, NH3, I have to do this problem twice, looking for moles of ammonia. All right, the first one, I'll go from moles of N2 to moles of NH3, ammonia. Right? And the second one, I do the same thing, but I'm trying to figure it out for hydrogen this time. So I go from moles of hydrogen to moles of ammonia. Okay? Now, can you help me with these? What's the ratio of moles of ammonia to moles of hydrogen in the equation?
There is 1 mole of hydrogen. No, there's 2 moles of hydrogen. 3 moles of hydrogen for every 2 moles of
ammonia. Very good. How about this one? Moles of ammonia to moles of nitrogen.
Same exact thing as the bottom one.
Really? Look at the equation well.
Wait, no. 2 moles of ammonia for 1 mole of nitrogen.
Very good. So, on the top one here, it says, what this is saying is, if you have 5 moles of ammonia, 5 times 2, you could get 5 moles of nitrogen. You could get 10 moles of ammonia if you had plenty of the other stuff. In this one here, it says if you get 3 moles of hydrogen, you're going to be able to get 3 times 2, 6 divided by 3, just 2 moles of ammonia. So both of those are telling you how much you could get if you just had those 2 components individually and extra of everything else. So in the limiting reagent problem, I do the limiting reagent reaction, and then I find the one that's the lowest. And the one that's the lowest becomes my correct answer, and the hydrogen gas becomes the limiting reagent. I know that the hydrogen gas, in this case where I have 5 of these and 3 of these, the hydrogen gas will run out first, kind of like the bread. I'll be left over with lots of peanut butter, right? The nitrogen gas will be left over. I'm not going to be able to get 10 of these. If I had enough hydrogen gas for all that peanut butter, then yeah, I could get more ammonia. But I don't. I only have 3 hydrogens. So 3 hydrogens will limit me to 2 ammonia. So because 2 is smaller than 10, I'm not going to get the 10. I'm going to get the 2. So for a limiting reagent problem, you have to perform the problem twice. Once with both the reagents given individually, and then find out which one is going to produce the least amount. And that'll be the amount that you'll produce, and that'll be the limiting reagent. Okay, very good. Next time we'll talk more about limiting reagents and solve some problems with them. Good job.